prefer to just have the answers given to them, or the students would prefer to have the answers given to them for the exercises. So that's what I've done. For the start exercises here, I've written out a solution. For those of you that have had a look on the website already, you will have seen them. They were handwritten, so my apologies for that. It's just a lot quicker to do it by hand than it is to type it up and draw nice pretty pictures and so on. I'm hoping that the meaning is there and that you can figure it out from what I've given you. The unstarred exercises, so this refers to chapter 2 of edition 3 of the text, for which the exercises are on the web as well. I'll bring them up in a moment. So the unstarred exercises, apart from the first one in this question set, have an answer provided at the back of the book. And I've copied that answer for you as well. But it only gives you the final answer. It doesn't show you the working, whereas my solutions to the start exercises show you the working as well. Which just reminds me of a point that I'd like to make to you guys, and I'm hoping that the message gets across to all of you in video land. For Lab 1, there's a number of questions where you're meant to derive simplified sum of product or product of sum expressions for the segments, say, of a 7-segment display. And I think you're asked to provide the truth table and to provide the minimized expression. Now, I don't know about you, but I don't necessarily trust just an expression being written down there. I want to know how that was derived. So, you know, if it's not obvious, if you can't read the expression directly off the truth table, and by reading off, I would mean that something like an AND function is pretty obvious, an OR function is pretty obvious. But anything apart from that is not necessarily obvious. Then I'd want to know, how did you derive that expression? Because otherwise, how do I know that you derived that expression, right? Does that make sense? Do you think it's fair to expect that? So although I haven't explicitly asked for it, I would be expecting that you do show you're working if there's anything that's non-trivial there. Okay, that's just an aside. So for these exercises, if I go back to the Week 2 entry for the exercises on the website, the problem set is provided there. Unfortunately, the way I photocopied the book meant that it didn't really come out in a very meaningful or useful way, but I can, because it's rotated, and I don't think I can rotate it just in Safari, but I can.
There was a option at the bottom.
Sorry?
If you open it on Chrome,
yeah. Yes. So I may as well open it in Acrobat and rotate the view, right? All right, so, you know, it's probably a bit too small for you guys to read it, but I think the first start exercise was which? Let's just go back to the start exercises. 2.3, right? Can you all read that, even at the back, the exercise list? Righto, so it's 2.3. So if I zoom in on 2.3, I'm hoping you can read this. Is that big enough? Can you read it at the back? Right? Good. So asks you to prove, looks like the consensus theorem, right? Note that this is a consensus property. Okay. I was just looking at the expression. All right, so that's the first starred problem that I expected demonstrators to go through in tutorials and so on previously. Anyway, the feedback that I got last year suggested, look, it's a waste of time going through these step by step, and you're fumbling about and you get it wrong half the time. So just put up the solutions and, you know, we'll be happy. right? Which is fine. It's not really the way I'd like to learn, but if you want to learn that way. So I'm happy to discuss any of these questions. So for example, let's go and have a look at, I wonder why that's called Hikes-Toad Chapter 2 problems. Anyway, let's go back and have a look at the solutions. Let's get rid of that. All right, so here's what I've written. Let's view that in the browser. So it's a little bit, I can make it a bit bigger. Can you all read that? The answer that I've provided here to 2.3? Which asks you to show that the left-hand side here is equal to this right-hand side. Which, there's possibly a few ways of solving this problem, but an easy way is to just use identity and expand that using complementarity. I don't remember the names of all of the axioms, so don't quote me on those. But essentially, anding anything with one doesn't change the value of it, and one can be expanded to any x or not x. Take whatever variable you need. But that then gives us these two expanded versions of yz, right? And of course, then we can group them, xy together with xyz, and not xz with not xyz, as has been done here, and factor out the xy and not xz terms to be left with 1 or z and 1 or y, which by the null theorem is just 1 in each case, and therefore we're left with the end down here, right? Are there any questions on that derivation? Right. Okay, I think I'm only getting 2 people giving me answers most of the time here. I'd appreciate more feedback if it's possible. So there's another theorem called the factorization, I think it's a factorization theorem, that was the one that we looked at prior to the consensus theorem. It might be worth your while trying a similar sort of proof of that theorem, okay? Because it's of a similar level of difficulty to prove that as it is to prove the consensus theorem. Right. So, to cut a long story short, I wasn't intending to go through these. I'm sort of going to leave it to you. I'm going to put up the solutions for next week's exercises at some stage before next week's Friday lecture. If I were you, what I'd suggest you do is give the start exercises a go. And this is what I would always have recommended my students to do. You've got to try to, the way to get the most out of a tutorial is to do the questions yourself first. At least attempt them. Then you know what you're struggling with and can ask questions about those specific points when it comes to the tutorial. If you come in unprepared to a tutorial, you're not going to get nearly as much out of it because you don't know what you don't know. So I would suggest for next week, try all of the questions, try the starred ones in any case, but by all means also try the ones that are not starred. I don't think there's a phenomenal number of exercises. I don't think it'll take you a long time to do. It might be an hour's worth of work, but count that as part of your study, right? Then at least you'll know what you don't know, and when we come to do our Q&A, you'll have some questions that you'll get an answer to from me, all right? Or I hope I can answer. So, given that's the plan of how I thought you'd get the most value out of this Q&A session, so I'll answer any question you've got about the course. I can't go much beyond the course. I don't necessarily know anything beyond that, but I need to try. I'm confident I should be able to answer most of your questions.
I have a question with the changing to using the NOR gates only, but it's for next week exercises. Can I also ask?
Well, we talked about it in lectures, so yeah, that's fair enough.
So in the fourth one, in that exercise, for one of the wires, it's connected to, it's a split between two wires, and then when we add the bubbles to an AND gate, it's only had one bubble, so we have to add one more.
Mm-hmm.
But would that extra bubble we add be before the split or like after the split?
All right, I don't know what the split is that you're referring to. You mean the wire that you're, well, okay, so you're saying that you have somewhere in your circuit, let me try and draw my understanding of what you've got, an AND gate, and it's feeding two sources, or two sinks.
At the back input of the AND gate.
Ah, it's a NOR circuit, okay. Righto, so you've got what? Well, that has to be a unique source, right?
It's a unique item.
So it might be sent to other gates, but
Yeah.
something like that.
Yeah.
Right, okay. This is the rest of the circuit down here, right? And so you're saying, I have to put a bubble there. Yeah. Well, you're free to choose. But depending upon what happens down here with the bubbles, right? If you have to add a bubble here to all of the other sinks of this wire, sinks of this net is what it's called, then you might as well put the bubble at the beginning, right? But if this is better off not complemented, well then it's better to put the bubble here. Does that make sense? Right. Okay, so are there any questions? How have you been going with the labs? All right, I want to make some more points that maybe were not made forcefully enough by me last week in the lecture when we talked about the labs and what the best way to approach things is. And I don't know what the demonstrators have told you. Okay, so the focus of the course and the hurdle that you have at the end is to pass this practical exam, right? There's a 40% hurdle on the prac exam at the end. The prac exam's worth 30%. So the 40 marks that you get from your labs, the progressive assessments that you get from your labs, while they'll count quite a bit to the final mark that you get, they do not guarantee that you pass the course. What guarantees that you pass the course is getting more than 40% in the prac exam and, of course, enough additional marks to pass the course. Very few people, very, very, very few people, you might have 1% would get more than 40 in the hurdle and yet not have enough marks from labs and quizzes and so on and the theory paper to pass the course. That's a very rare event. It's probably less than 1%. So the focus really is on the practical work in many, many ways. While we give 4 hours a week to lectures, those lectures, as I've tried to explain, provide the theory that you need to understand the work that you're trying to accomplish in the lab and the sort of circuits that you're trying to build. That's the background for them. So there's 7 labs, there's 9 weeks effectively over which those 7 labs are conducted, submitted, and assessed. So you really only have 2 spare weeks over the whole 9-week, or the remainder of the course, right? 2 spare weeks, as far as labs are concerned. Every week, effectively, except for 2, you're getting a new lab. So if you want to finish the labs and be on top of the lab work, best thing is finish them the week you start them. If you let them drag out, or if you delay starting until just before it's due, then you've already burnt that 1 week. That only leaves you 1 more week. And you'll be catching up all the time. So the only way that you can be sort of know that you're on top of things is to try and finish each lab the week that it's released. That's the best approach, okay? I hope I make that message clear. So better not to leave, finishing this lab until the weekend before it's due, which is next weekend, right? Okay, are there any questions on that? Yeah?
Question, which is more of a curiosity and not super essential, but how are the labs marked? Like,
Right.
you're going to boot up Vivado on every single thing and I think they're going to put it on the basis board for every single thing, or they're
Yeah.
just the code?
If it's something where you've got to, where we say you've got to test your circuit, we generally do that. Like for some, it's not necessary. You know, as soon as you open the file, that it's not going to work. It's not going to run. It's not going to compile, right? But if it looks like it's going to compile, then we do compile it, because that takes time, as you know. It takes like a minute and a half sometimes. And then we do load it to check that the logic's correct. I mean, for the simple early ones, it's pretty easy to see whether the output's going to be right or not. But for the later ones, the logic begins to be a lot more complex. You've got modules, or many more modules involved. It becomes too difficult to do that by visual inspection. You have to run it. Yeah. And the simulations are like that too. When you get to those, we have to run them. But in essence, be guided by the number of marks allocated to each part. That's how many marks there is. You will get feedback on your submission. You'll get, you should get feedback. You're entitled to ask for feedback for every deduction that you got. But the tutors, the demonstrators have been told that they should be providing reasons for the mark deductions, okay? Is that enough? Is that what you wanted? Any other questions on anything?
It's about the midterm, so it will have like contents of week 1 to 5.
Yes, it will.
Will it be like MCQ or writing it like exam driven?
It'll be multi-choice, yes. 45-minute multi-choice in this room, unless I can find a larger room. So I'm hoping that 30 people don't turn up. Rather than only 30 people showing up. Yeah. Any other questions?
For the final, how hard the practical one? How hard is it compared to the lab? In terms of like
There's a sample paper on the website, right? Have you had a look at it?
no.
Have a read. It wasn't last year's, I think it might have been the year before's final exam. Yeah.
So most of the coding stuff, are we meant to just pick it up from the labs itself, or will it
Yeah.
make more sense in the
No, you won't need more than what we talk about generally. So I don't think I made explicit mention of it this year. I have done so in the past. I'm not like, I know that a third of the class are comp sci students and a third are software engineering students, and I'm a computer engineering teacher. I'm not teaching, I don't know what you are, but I don't teach Bacchus now a form for VHDL or anything like that. I see that as pointless. It might have some point right in the very last lecture because you'll have seen the majority, but not everything in VHDL. VHDL is a very large language. The spec is publicly available. Go and download that if you want to really know the ins and outs. So what I do is I'm teaching it by showing you examples, by example, right? So I'm hoping that you pick up enough from that. That's the way. If you're not being formally taught a language, you would normally learn that language. Okay, so I don't think you need anything beyond what I cover in some way in the lectures. Any other questions? Right. Okay, so I don't know what would be hard or easy for you, so you're going to have to go through it. And of course, next week I'm happy to come back to look at questions that were unclear to you, but I would suggest try the questions yourself and have a look at the answers I've provided to see whether or not that makes sense to you. And as I say, I'll put up the answers for next week's start exercises at some stage prior to next Friday. Right, so we've only spent half an hour, or less than half an hour, doing Q&A. Are there no other questions? Do you want me to show you anything? Right, you're meant to do some of these from 2.7. So the ones that are starred here in the textbook, they're generally the ones that have an answer at the back end. So 212 is one of the problems that I've not starred because 212 has an answer in the back of the text. So the back of the text, I've photocopied those answers here. Here's the answer to 212, right? So you can do the problem and see, what did you get? Okay. So that's what I've done for each of the set of exercises effectively. And in principle, while they're not, I've already told you that the midterm quiz is multi-choice, so while these are not of the style or not exactly the way that the midterm quiz questions would be posed, I think you should be prepared to be able to answer questions of this difficulty, because if you can do that, you shouldn't have any problems in the midterm quiz. And the same goes for the theory paper at the end of the year. It's only a 1-hour paper at the end of the year, and it's open book. So you can bet your bottom dollar there'll be no questions at the end of the year, in the final theory test, that are in the book. You know, wouldn't be much point. All right, okay. So if there are no further questions, yeah.
One last question. For the sample paper, will more be released towards the end?
No, I feel that's enough to show you what sort of difficulty and what the format is. You can imagine that the paper you will get has exactly the same, pretty much, if not exactly word for word, the same instructions. It'll be a different question though. But that gives you a sense of the sort of problem that I expected people to answer 2 years ago. I don't know whether I should make any further comment at this stage. But given that I haven't been asked, I won't comment. Right. So what I have done is prepared the first half of the next lecture to give to you this afternoon. That probably won't take more than an hour or so, so we'll have plenty of time and you'll get an early mark once again today, unless there are any further questions. So, given that there isn't, let's get into this then. All right. So, in the first two lectures, we talked about Boolean functions, or what's known also as combinational or combinatorial functions, and simplifying those, and techniques that we can use to simplify them. And we've looked at multiple ways that they could be implemented, both in various sized lookup tables, which is sort of the raw logic resource in FPGAs, or as NAND and NOR only gate circuits if you were targeting some sort of ASIC process or custom VLSI process. We're going to shift a little today to really answering or laying the groundwork for what you'll need for Lab 2, where you do need to create some addition circuits. So this is the theoretical background that you need for that. And then we're going to come back to more general sort of combinational components that are, well, combinational components that are used in larger digital systems. But that will be covered in lecture 4. So we'll start talking about that probably on Tuesday next week after I finish this lecture. So what I want to achieve in this lecture overall is to just review how integers are represented in computers. And then we'll focus on circuits for performing arithmetic operations, whereby in this lecture all we're doing is looking at addition. We will look at multiplication and division, which are more long-wielded and complicated operations in later lectures. We'll also talk more about VHDL. You'll see a number of new aspects that you may or may not have already been exposed to in the lab. This will definitely bed that down. And finally, we'll talk about how you can change the architecture of a circuit in order to make it perform better. All right. There's various types of numbers that we use in computing, as you know, where we deal with both integers and floating point numbers. In this course, we won't worry about floating point representations, but you can think of floating point representations as just being more complex applications of what we're doing here with integers. It's slightly more involved. I think that gets covered in a number of successor courses like COMP and 3601 and 4601. All right, so an unsigned binary number usually has this sort of bit stream representation, where the least significant bit is over on the right, most significant bit on the left. For an n-bit number, it looks like this. And that, of course, has the value, which is given here in this long and unwieldy expression, where essentially every one of these bits is used to scale the corresponding power of 2, and they're all added together. That's the resulting value of that binary number. And this is just a shorthand way of expressing that. I think there should be little doubt in your minds that that is true, even if it's presented in a fairly dense slide here. And of course, we don't have to restrict ourselves to binary. We could use any radix here, any radix R, which ranges from 0 to r minus 1, where each digit is going to have the value 0 to, some value between 0 and r minus 1. And the subsequent value of that number is just each digit scaling the corresponding power of r being summed together to give us the overall value. That's all complex formal ways of expressing pretty simple ideas that should be familiar to you from this table here, namely that apart from decimal, which we're familiar with, and binary, which you are reasonably comfortable with, we also normally might use or rely on base 8 and base 16, or radix 8 and radix 16, namely octal and hexadecimal, to represent numbers, whereby octal and hexadecimal respectively just combine either 3 or 4 bits at a time to represent the value that that corresponds to. The decimal value gives us what the corresponding hex or octal or binary representation looks like. Okay? So they're commonly used. One thing I'm not going to go over is how to convert a decimal number to a binary number. Are you all familiar with how that's done? Have you seen it before? Have you done it before? Okay, just be clear, revise it if you haven't. The web explains it anyway if you can't find it. In fact, the web explains most things that aren't explained very well by me. Right, what's that? Some big mosquito. Okay, so let's talk about addition and adding bits together. So if we've got two binary bits, either 0, 0, 0 and 1, 1 and 0, or 1 and 1, together they end up adding to a so-called sum bit, which is the rightmost bit, and a so-called carry bit, which is the left bit. As you can see in all 4 possible cases that we have listed here. In a truth table form, I've just translated this over into the truth table. There's sort of a transposition of those results. Note that it doesn't really matter which order X and Y. We could swap these 2 columns and you'd get the same result coming out. So the table's symmetric with respect to X and Y. And the other thing that's worth noting is if you think of these 2 bits as being a unary number, what's a unary number? Like chalk marks on a wall, where you simply count the number of ones here. No marks gives us a total sum of nothing. 1 mark is 1, here's 1 mark, and here's 2 marks gives us this value. So you're converting a unary value into a binary value, effectively. Now, this function that you see over on the right here, the sum function, is the so-called exclusive OR function, which we've mentioned, some of you already know about. And in essence, the difference between exclusive OR and OR is that the condition that both X and Y being 1 is also true for OR is not the case for exclusive OR. For exclusive OR, we're only allowing one of the 2 operands to be 1 for the exclusive OR function to be 1. Okay? So we can draw that as a gate as well, but I've got something else to say about that in a moment. There's a little star up the top there. So this is the circuit that implements this function, and it's known as a half adder. And hence, its graphical symbol looks like this. It's just a box, 2 inputs X and Y, 2 outputs S and C. You can also think of this as a block diagram, and how you would use a half adder in a block diagram. What is really important to note, and I will mark people down if they don't understand this idea is that this exclusive OR gate is a lot more complex. There is no single gate that is an exclusive OR gate. It's really just a symbol that we use to represent the exclusive OR function. Because to implement this function, not x, y, or x and y bar, right, we need two AND gates and an OR gate, right? So, and that's a two-level function, whereas this is just a single-level AND gate, right? So it's a lot simpler. So I hope you appreciate that this gate is not a simple gate, all right? So it really represents an assembly of AND or NOT, or NAND and NOR gates. It's not just a single gate. There is no single exclusive OR gate, as it were. Okay, so they have more complexity and delay relative to simple gates like AND or NOT, NOR and NAND. Okay, so in general though, we want to add more than 2 bits together. We want to add binary numbers together. Here's an example of 2 5-bit numbers being added together. And that requires us in every bit position to now add these 2 bits together, but also to take account of a carry, a possible carry from one bit position to the next. So in this particular case, when we add 1 and 0 together, we get a 1. And in the next bit position, when we add 1 and 1 together, that's of course a sum of 0 and a carry of 1. The result's 2, so it has to be binary 1, 0 as the result. So the carry that we get in this case is a carry of 1, and the sum bit is 0 down here. So this carry bit is added to the 2 bits that we next want to add together, namely 1 and 0. So we've effectively got 1 plus 1, which is 2, so again a 0 plus a 1 carry. Then we have 3 ones that are being added together, so of course the sum of those is going to be 3, or a sum bit of 1 and a carry bit of 1, right? So finally we see that over here on the right-hand side. Is that clear? All good? No questions? Good. All right. So let's have a look at that. Adding these 3 bits together, 2 operands, an X bit and a Y bit, and a carry in from the less significant bit position. So that's what I have listed here in my truth table: the X, Y, X, the ith bit of X, the ith bit of Y, and the ith carry, the carry into the ith bit position. That generates a sum in the ith bit position and a carry out into the I plus 1th bit position, right, to its left. Here are the resulting expressions. I only have 1, 1, so that's 1, 1, 2 here, so 1 and 0, 1, 2, so 1 and 0, 2, 1 and 0, 3 ones, so it must be a 1 and a 1, right? So the unary value again is being converted into a binary value here. So how do we represent these expressions? Well, we want to simplify them as much as possible. And if we try and map out the sum bit, so this function here into a 3-variable Carnot map with x, y being the more significant and carry being the less significant bit, doesn't really matter which order we put them in, you're always going to get that bit pattern coming out. It's a checkerboard pattern, right? And if we've got a checkerboard pattern in a Carnot map, there's nothing we can do. We can't simplify. We can't combine. There's no neighboring ones that we can, either horizontally or vertically adjacent, that we can combine and then use the uniting theorem on to simplify. And so all we can do is list out all of those min terms that are covered. But what we can do is factorize. We can see that these first 2 terms have, these 2 terms have not carry in. So xi bar and yi, or xi and yi bar, are ANDed together with not carry in, which is the first part here. And down below we have not xi, not yi and ci, or not xi or yi and ci. So that's that bit down there. And we can tell that one is the complement of the other. That's possibly easier to see from the truth table when if Ci had been the leftmost bit position, it would have been easier to see this. So for all of the rows that have Ci equal to 0, we have 0, 1, 1, 0. So it's the same actually as the bit pattern that we have there. And for all of those where Ci is 1, we have 1, 0, 0, 1. So actually it's the same bit pattern as I have here. So you should be able to see that the top half is the complement of the bottom half. And therefore, I argue that xi bar yi or xi yi bar is the complement of not xy, not yi, or xi yi. So they're complements of each other. One is the exclusive OR and the other one is the exclusive NOR. And so then we're left with exclusive OR plus and Ci bar, or not exclusive OR and Ci. So it's the same as not A, B, or A, B, B bar, which is just exclusive OR again. And hence we can see that this is just the exclusive OR of all three variables. And we can show by associativity that it really doesn't matter where those parentheses are. In fact, we don't even need the parentheses. Okay? The associativity allows us to group these terms together in any way whatsoever and write them any way we like. We can write x, y, c, or x, c, y, or c, y, x. It's up to us, right? Makes no difference. Because of the fact that this function is 1, when there's an odd number of inputs that are 1, it's also called the odd function. All right, let's turn our attention to the carry. Okay, in the top half here we see the and in the bottom half we see or. But that's if we use xi as the variable that determines that we're factorizing out around. Let's not do that. Let's have a look at when we map this into the Kano map, 0, 0, 0, 1, 0, 1 over here, and then 1, 1 here, then we can combine, well, each one with its neighbour, thereby have a slightly simplified expression that we have down here. That the carryout is xi and yi, or xi and ci, or yi and ci. For 3 input bits, that's called the 3-bit majority function because it's 1 when 2 or more of the input bits are 1. Okay, which stands to reason because when the sum, this unary sum, the sum of the 3 unary bits is 2 or 3, we need to have the carryout being 1, right? Okay, good. So that's that. Are there any questions on the derivation? Okay. So the circuit diagram here, we show a 3-input exclusive OR. Remember that that's a bit of a complex gate. And the lower part, so to derive the sum bit and to derive the carry out bit, or the carry into the next more significant bit position, we just have the sum of products formulation that we've derived. The graphical symbol for a full adder, it's called a full adder because here we've got, you know, a carry in and a carry out. 3 bits looks like this. I'll show you another reason why it's called a full adder, and that is because it's composed of 2 half adders connected up in this particular way. And the way you can understand that diagram above is by looking inside each half adder. What circuit is that? Well, we can see here then that the output SI is just the exclusive OR of XI, YI, and CI, right? Which is what we previously derived. And as for the carry out, well, here's the XI, YI coming out. And for this, well, we have the exclusive OR of xi, y, so we know either x is true or y is true, and we're ANDing it together with ci. And that gives us this expression here. And you can formally prove that too by playing the same trick as we played with the consensus theorem when we had a look at that, simply by combining xi, y with c or c bar. That then expands the expression, and you can prove, you can, what did I want to show here? Well, that equates to these terms over here. Sorry, I think I've made that a little bit more confusing than it needs to be. What I meant to say was that the output of this exclusive OR gate here is xi, yi, or xi bar yi, and then we're ANDing that together with ci, right? So we've got ci, xi, yi, yi bar, or ci, xi bar, yi. And I'm ORing to that xi, yi, right? So that's my expression for ci plus 1. And this reduces to this expression by ANDing this guy with c. So what I want to do is show that this is equal to this part, or ci or not ci, xi, yi. Right? Would you agree? And then I can take ci, xi, yi, and then AND that together with ci not xi, yi, and I'm left with ci, yi. And I can take not ci, xi, xi, yi, and combine that with, where am I? Sorry, I can combine ci, xi, yi. Well, I can combine ci, xi, yi with both of these terms to get, in this case, ci, xi. I'm left with ci, xi, ci, yi, and finally just xi, yi over here. I still don't know that I made that a very clear explanation. I'm hoping that you can see my logic though. Is this clear? So what I've derived here is actually the circuit output, namely ci, xi, yi bar, or ci, xi bar, yi bar, yi, which is the AND of this exclusive OR gate coming out into this OR gate. And of course, the other input to the OR gate is the xi, yi that I have here, right? And I've simplified that by ANDing xi, yi with ci or ci bar, and then using the uniting theorem on ci, xi, yi with ci, xi not yi to eliminate yi here. And I've used the combining theorem with ci, xi, yi and ci, xi bar, yi to eliminate the xi bar to get ci, yi. And then finally just ANDed it with the xi, y that I already have. Okay, so that gives me that three-term simplified form. Is that clear? Yeah.
When do we get the first two terms? Ci, xi, yi bar, and ci, xi bar, yi. Like the first two terms.
These two? From here, because that's the output of this exclusive OR gate is xi, y bar, or xi bar, yi. And that gets ANDed here with ci. Yep, got it? Any other questions? Yep.
Where the last term comes from?
Which last term? This xi, yi?
Oh no, ci plus ci bar x.
Right, because what I've done is I've ANDed this with 1. That's equivalent to 1 and xi, yi. So I've just played the same game as I did with the consensus theorem proof. Yeah? Okay. Any other questions? Okay. How are we going? Right. One more thing to talk about, and then I think we might just have a break. So, gates are made out of transistors, but transistors have capacitance and resistance associated with them. And so because of that, those of you that have done a bit of circuits know that there's a time constant associated with charging the gate up or with decharging, with what's it called when you let the charge go? Discharging the gate. That's it. Thank you. So, you know, gates do not actually instantaneously change, but rather there's a period that it takes for them to charge up, and there's a period for them to decay, like that, if we're going between logical 1 and logical 0. And this is normally these days about, well, 0.7 volts, 0.5 volts, something like that, right? So, because of that delay, and if we're combining gates together, it takes us time for signals to propagate through the structure. So I have a question. What are the gate delays in computing Si and Ci plus 1 here? And there's no closed answer to this. There's many answers. So for example, I see that the shortest path between the inputs and Ci plus 1 is at least 2 gates, right? It could be more than that if we're coming through this path here, right? So the upper path through this AND gate and the lower path through X1, the lower AND gate is 2 gates, but we've still got this exclusive OR gate, which is at least 1 gate delay, and I'm going to tell you that it's more like 3, usually. So when I looked it up, actually, I got the impression that this is probably going to be, at very least, about 120 to 130 picoseconds for 65 nanometers, where it's only 20 to 30 picoseconds for 65 nanometer AND gates. So there's about a 3-fold difference in delay. And as for the delay for the sum, well, it's at least 2 gate delays, but we know that this is a bit of a fake, that this is not single gates. We're probably talking more like 6 gate delays, so it's quite a large delay that we're talking about as far as getting the sum out. Does that make sense? So if I change one of the inputs, what does that mean? How long does it take for those changes to be reflected in the outputs? And how does it look? Well, it would seem that it's going to take some time before CI changes, potentially, and slightly longer before SI changes, right? Okay, now bear that concept in mind, because what we want to really do is add 2 n-bit numbers together. And to do that, we use a structure. The simplest way to do it is to use a structure that's called a ripple carry adder. I'll show you why in a moment. But that essentially just strings together a whole chain of these full adders. And at every stage or bit position, we add the corresponding bits of the operands together, and we take the carry in from the less significant stage immediately to your right to produce a carry out to the full adder to the left, a more significant full adder to the left, and so on, right? Some of you want to leave, so let's have a break and we'll resume in 5 minutes. All right. Let's continue on. Okay, so does this structure make sense? That this is how you might add two numbers together. So you've got n-bit inputs, x and y, from least significant bit here to most significant bit over on this end. And you add them up sequentially, well, conceptually, sequentially. We add x0 to y0, that produces a sum bit and a carry out, right? That gets added together with the x1 and y1 bits to produce the sum bit at position 1 and a carry out to position 2, and so on, right? All right, so when the operands x and y are applied to the adder, it takes some time for that output s to be correct. And the reason for that is that the carries have to be determined before you can determine what the sum is, right? Because the sum is dependent on the carry. So if the time to produce the carry out from this first stage here is delta t, and it's the same for every stage, it's going to be n delta t before we know what the carry into this stage is over here, right? Or rather out of this stage. And it's only at that point in time that we can compute all of the sums. So only when you receive the carry can the final value of the sum, the actual value of the sum, be determined. All right? And so the delay in processing each stage gives rise to the name of the adder. It's called a ripple carry adder. And you can understand this by thinking about the following scenario. Let's say the value x is 0 in the most significant bit position and 1 in all other bit positions. And the value y is 0 in all bit positions, right? Well, then the sum should be 0 in the most significant bit position and 1 in all of the less significant bit positions, because we're just adding 0 to x, right? So the sum should be x. But if I change y from being 0 in every bit position, just to having a 1 in the least significant bit position, just over here. That's the only change I'm going to make, is flip that bit from 0 to 1. Then the sum has to change completely, because now I have x is 1, y is 1, the sum has to go to 0. It was 1, it's got to go to 0. And of course, my carry now, which was 0, has to go to 1. Then I have a 1 coming in here. I've got a 1 at x, add together, that becomes a 0. That produces a carry out of 1, which has to continue on. So you see these carries are then going to ripple through the adder. And so the sum, the final version of the sum, is going to actually also be derived from least significant bit through to the most significant bit, one bit position after another. Okay, each one with a delay associated with it of about delta t. So the sum is going to flip over from 0 and all the other bits being 1 to having a 1 in the leading bit position and 0 in all the others, but that's going to happen over time. Is that clear? Looks like I get no nod, so no general agreement on this, except for one person. Are there any doubts about this? So this is a long chain, and would normally be 32 at least, but it might only be 8. But it's normal that we're adding 32-bit integers together. And it takes quite some time for the sum bits to be resolved if we use the architecture that's illustrated here. And that's a consequence of it taking time to compute a carry into each bit position, which we know is vitally important to determining, what the sum should be. Right? We have this expression here for the sum, and that has the carry in linked into it. So only when we know what the carry in is can we compute what the sum should be. So since it takes time for those guys to arrive, it's going to take time for the sum bits to be derived. And they'll be derived one after another from the least significant bit position all the way to the most significant bit position. All right, let's have a look at a bit of VHDL. So if you wanted to describe this full adder, the circuit that we considered previously, it's pretty straightforward. We've got 3 inputs, Xi, Yi, and Ci, and 2 outputs, Si and Ci plus 1. Let's call them carry in and carry out, just to keep it a bit simpler. And the architecture just has these 2 concurrent simple signal assignment statements. S is the exclusive OR of X, and Y exclusive OR with Cn. XOR is a binary operator, so we can write it this way. We don't need parentheses because exclusive OR is associative. All binary operators are associative. So if that's the meaning that we want for a 3-input exclusive OR, it doesn't matter what order we list them in, and it doesn't matter where we put the parentheses. For carry out, it's literally just the sum of product expression that I have depicted there. So that's pretty straightforward. What begins to be more interesting is how you then build a 4-bit adder, let's say, from that full adder. Here is the code for our full adder at the top here. So that's the design entity called a full adder, right? The entity which has our ports and the architecture which has our 2 expressions in it. And we're going to use that as a component in a 4-bit adder. So what would a 4-bit adder have as its inputs and outputs? Well, it's got to have the 2 operands, X and Y, the respective bits as inputs. It's got the 4 bits of the output, and it's got to carry in so that we can chain 4-bit adders together, and it's got to carry out so that we can chain 4-bit adders together, okay? As to the architecture of the 4-bit adder, well, we want to use the 4add component, and so we have to declare that in the declaration part of the architecture. And in order to connect our full adders together, we need to declare some internal signals. The C1, C2, and C3 signals that you see up there. Right. Just take a photo of this, and then I can scrub it. This looks very good. Right. So what we're going to do is we're going to build a 4-bit adder, by having 4 instances of an FA component. Right, and we have to connect those together. So each one has a sum bit coming out. Let's call this 0, 1, 2, and 3. So we have carry 0, but that's going to be an input to this guy as its carry in. So we're going to call that C1. Actually, this should be called C1. C1. And we have x0, y0 coming in, and, well, that's a 0. Well, actually, the way that it's listed here, it's going to be Cn coming in as the carry into full adder 0. So to connect these full adders together, we have to have those 3 signals declared up the top here, right? And having declared the component that we want to use within our architecture, we can then instantiate any number of copies that we would like. In this case, we're instantiating 4 copies, and we're naming them stage 0 through stage 3, respectively. And we make what's known as a port mapping, associating with the declared ports that we have for that component with the ports that we have for our design here. So we have C in and C out, and X0 through X3, Y0 through Y3, and S0 through S3. So for our 0th stage, which is the least significant one that we have up here, we want to associate X0 and Y0 and the overall carry in that we have down here with the carry in, the X and Y ports of our full adder, and S0 is the output of our first stage, and C1, this internal signal, is the output, the carry output of this full adder that we have up here. So we could keep on going. We're going to have X1 and Y1, X2 and Y2, and X3 and Y3, and we have our carries connecting up these full adders, respectively C2 and C3, and we have S1, S2, and S3 being produced, as well as C out from our final one. So that's the structure that is being created here. There's 2 different ways that you can instantiate a component, as you see here. There's a so-called positional association with named ports, where simply the same order is maintained as is declared for the component. But there's also this so-called named association, where on the left we have just the names that were provided for our component, and on the right we can associate which port we want to associate with it, whereby the order in which you list the ports can be arbitrary. You don't need to know what order they are in the component. That's helpful when you're designing something you haven't finalized how you're going to declare the component that you want to use within your system. Okay, so there's a few new things here that you probably haven't seen too much of yet. The fact that we have to declare a component within our architecture, that we have a number of named instantiations, so labeled instantiations, with 2 different port association methods. We declared our component full add in the same source file as we declare our full adder. Because of that, we have to have a separate library, IEEE, and use IEEE Standard Logic 1164.all line ahead of each one of our designs or design entities within the VHDL file. Okay? You haven't seen the declaration of internal signals before, so that's done there as well. And this is the structure that results from doing this. Are there any questions about this? Yeah.
When we full add the first one, how will we know the value of C in? Isn't it always just going to be 0?
Well, we don't know the value of C in. We do for the other stages, but C in is going to be given to us by the environment. Whoever instantiates full, adder 4 is going to connect to C in. So in your case, if you were testing this design, you could connect switch 0 to C in. Right? Any other questions? All right. Because this can be a bit annoying, and there are components that you want to reuse in different projects. What you can do is put all of the components that you want to reuse into a package, so-called package, just like the IEEE Standard Logic 1164 package gives you all access to all of the standard components that are available for that standard logic. For example, how is a plus sign interpreted? That's all hidden inside this package. You can declare your own package. This is a user-defined package, in this case just calling a full add package, which contains in it the component declaration that appeared in the architecture that you saw a moment before. This appears at the end, say, of a big source file that has all of your component descriptions, the entities and architectures of those components, and then you just create a package that has everything in it. Or you might create sub-packages that have less things in it. Doing so then allows you to avoid having to declare the component in the architecture part of your design, and it allows that component to be reused across multiple projects. So this is a useful thing to do. How that impacts on the design is as follows. We would then have an extra package that gets included at the top. It would be, because we define that in our own working directory, we would say it's work.fulladdpackage.all. .all means we want all of the components from that package. You can nominate which components you want to make use of. Note then, though, that the architecture doesn't have to redeclare that component. It's assumed already declared, and therefore we can just instantiate it as follows. So that's the benefit of doing so. Another VHDL feature makes life a lot easier. Rather than having to declare the individual bits of a number, you can declare vectors. So X and Y can be declared as standard logic vectors. Here of size 3 down to 0. Now I know you've already been doing that within your first lap, actually, because you've declared the switches and LEDs as being vectors. This tells us that there are 4 bits. It tells us when you go 3 down to 0 that this is meant to be interpreted as a numerical value, in contrast to the signal C here, which, remember, are just the individual carries. So there's no direct relationship between one carry and the next. And so that assembly of signals can be declared rather than 3 down to 1 as 1 to 3, thereby indicating that that's not a numeric value. It's simply a collection of signals, potentially unrelated. This is used to create buses, for example, as well. That then makes the entity a lot neater, a lot easier to understand, and of course then we simply have to be careful about how we nominate the individual bits of those vectors to be the inputs and outputs from our full adder components. Yeah.
Sorry, how is the 3 down to 0 and 1 to 3 different again?
Well, when you use the down to word, that generally means this is a numeric value that we're going to be using. 3 down to 0, that's just the way you declare a numeric value. Whereas 1, 2, 3, when you go up rather than down in the way you identify the individual bits, that then refers to non-numeric signals. Signals aren't necessarily numerically related. All right, I've only got a bit to go now, for today anyway. Right, so far we've been looking at unsigned numbers and how to add them together. I want to shift gears to look at signed numbers as well. So you're familiar with unsigned integers. Perhaps you're a little less familiar with signed integers, although the concept is probably known to you, that you then have to have one of the bits dedicated to telling you is it positive or negative. And there's various ways that you can then interpret the magnitude of the number that's left. So 3 common ways are to just use sign and magnitude. In this case, the leading bit just tells you whether it's positive or negative, and the magnitude doesn't change. You use the same value whether it's positive or negative. So positive 3 would be 0, 0, 0, all the way down to 1, 1. Negative 3 would be 1, 0, 0, 0, all the way down to 1, 1. 1's complement subtracts every bit from 1 effectively, which is the same as subtracting the number overall from 2 to the n minus 1, so the n-bit number from 2 to the n minus 1. That's the same as flipping every bit. So the negative value or the complement of a particular value is determined by simply flipping all of the bits. So 3 would be 0, 0, 0, 1, 1. Minus 3 would be 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0. Then there's 2's complement, and this is the one that we'll be using and is most commonly used. We'll see why in a moment. It's essentially the same as the 1's complement with 1 added to it. So it's k1 plus 1. So instead of subtracting the positive value from 2 to the n minus 1, we're subtracting it from 2 to the n. So it's a bit like subtracting a 3-bit number from a 4-bit 1000 value. So it's equivalent to flipping every bit and then adding 1 to the result, which could of course be quite complicated if there's a long string of 1s. Okay? So let's have a look at how they differ when we represent them. Here's the bit stream for the 16 least significant. Well, they are all there actually. They're just not in order here. We've got 0 through 7 up the top and 1, 0, 0, 1 through 1, 1, 1, 1, 1 down the bottom here. The positive values are the same for all 3 representations. The negative values differ a little. So sign and magnitude, leading 1 tells us negative, and then there's 0, 0, 0. Well, it must be negative 0, negative 1, negative 2, and so on. 1's complement, you have to complement every bit. So what's this number? Well, it's 0, 1, 1, 1. So it's 7. So it's negative 7 that 1, 0, 0, 0 corresponds to, and so on. To derive negative 7 in 2's complement, though, we have to take that value and add 1 to it. So it becomes this. So that's my minus 7 in 2's complement, right? Which means that this is minus 1 in 2's complement, whereas it was minus 0 in 1's complement. And that leaves one value free, which is actually minus 8 in 2's complement. And so we see that sign and magnitude and 1's complement have 2 zeros respectively, and 2's complement only has the 1 0, and it has an expanded range. It goes from positive 7 to negative 8, okay, for 4-bit signed value. Just as a quick algorithm for deriving the complement of a particular bit stream in 2's complement. So the algorithm is here in blue, from the least significant bit position to the most significant bit position. Copy all the bits of B that are 0 and the first one, the rightmost one, and then complement all ones or all bits that are more significant than that first one. So for argument's sake, let's take this bit stream here. This 0, leave it. This 1, leave it, and complement the other 2. So the complement of this bit stream is 0, 1, 1, 0, which would be 0, 1, 1, 0, which is 6. So this is actually minus 6, right? So if I want to find what's the complement of, I don't know, 4, for example, it would be 0, 0, 1, 1. So 1, 1, 0, 0 is minus 4, as you can see. Right? So that's the way you complement minus in 2's complement. How do you add numbers together in 2's complement system? Straightforward. It's exactly the same way as we've added so far. Here's 4 examples that take the 4 possible cases. These are just 4-bit numbers, so the range is from +7 to -8, right? So if we add 5 and 2, it's just the same way we did it before, same with -5, which is this bit stream. Obviously, 5 has 1, 0, 1, 0, so the rightmost one stays, everything else is flipped. Adding them together gives us 1, 0, 1, 1. What's that number? Well, that's 1, 1, 0, 0, so it's -3. Okay? As for adding -2 to +5, well, that's -2. It's just add things together. We do get a carry out, and we can just ignore that. We don't need to worry about it. And if we add -2 to -5, which is these 2 strings being added together, again, we get a carry out, which we can ignore. And the result is 1, 0, 0, 1, which is literally just 1, 1, 1, 0. So that's -7. Okay? How about subtraction? Well, to perform subtraction, it's best just to complement the subtrahend and perform an addition. So if you want to subtract -2, complement the -2, that's 2, and add them together. That gives us the result. Same here. If we're subtracting a positive number, we'll complement the number, so 2 becomes -2, and add it together. Gives us a result. Ignore the carry out. Always ignore the carry out. Don't need it. Okay, so that's pretty straightforward. Since we can ignore those carryouts out of the most significant bit, we can use the same hardware, the same method for adding numbers together or subtracting them in 2's complement. So this is the circuit for doing that. It comprises this n-bit adder. That's the graphical symbol for an n-bit adder. It's this rhomboid with a notch out of it, right? Parallelogram. No, it's not a parallelogram, it's a rhomboid, right? With a notch out of it. That's an n-bit adder. So one of the operands on one side, the other on the other, and the sum out the bottom, carry in on the left, carry out on the carry in on the right, carry out on the left, usually. However, because we want to both add and subtract, we have to be able to either add y to x, or we have to be able to add the 2's complement of y to x. So to form the 2's complement of y, we form the 1's complement, which is just flip every bit, and add a 1 to it. And the way we do that is we use an exclusive OR gate as a conditional inverter. When the second input is 0 to the exclusive OR gate, it just passes through the input bit, the other input bit. Y, B becomes Y. But when this other input is 1, then it'll flip every bit of Y. So this will become Y bar. So B will become Y bar. But because when we also have to add 1 in, and we use the carry in to add that in as well, thereby converting Y bar into -Y, which is the 2's complement of Y. Okay, so it's quite a neat trick to do this. At least I think it is. I hope when you think about it and reflect upon it, it seems like I've talked too much. You might also think it's quite nice. So the take-home message is try to develop circuits that are as reusable as possible. Just like if you're developing software, you try to develop functions that you can use as much as possible. But if it's mechanical stuff, you develop tools that you can use for as many applications as possible. That minimizes the number of gates and the wiring complexity. I'm sorry to keep you. There's one more slide. Do I have any questions? Stunned mullets. Does everybody know what a mullet is? It's a fish. Okay. Obviously that fell flat. It's like a flathead joke. All right. So the last slide is just, okay, I've said ignore the carry out. It is important for one thing though, this carry out, at least one thing, and that is in order to detect overflow, we need to know what that carry was. The other important reason for hanging on to that carry out is if you want to make a 2n-bit adder, the carry out of the less significant adder becomes the carry in to the more significant adder, right? Okay, how do you detect overflow? Well, when we add 7 to 2, that gives us 9 as the result. We can only represent positive 7 with a 4-bit value. So we know this negative value is an incorrect result, right? That's because we've had an overflow. When we add 2 to negative 7, the result's negative 5. There should be no overflow. This should be fine. Adding negative 2 to positive 7, we should get positive 5 as the result. That shouldn't give rise to an overflow. But when we subtract 2 or add negative 2 to negative 7, the result becomes minus 9, and we can't represent that. So that should give rise to an overflow. And the way we could detect when an overflow has occurred is by looking at the carry into the sign bit and the carry out of the sign bit. In this particular case, we get a carry generated in the second bit position. That gets propagated in the third bit position into the final bit position here, the sign bit. So we get a carry in of 1, but a carry out of 0, right? When things worked over here, we had no carry in and no carry out of the sign bit position. Over here, well, we know we must have a carry into the sign bit position from this bit position because both bits were 1. So we have a carry in, so the 1 gives us a 0, and we also have a carry out, so there's no overflow, and the carry in and carry out of the sign bit position are the same. For this condition down here, there's no carry into the sign bit position, but there is a carry out. So what characterizes an overflow is when there's an exclusive OR between, when the exclusive OR between the carry into the sign bit and the carry out of the sign bit is 1. And in general, for an n-bit signed integers, when there's the exclusive OR between the carry into the sign bit and the carry out of the sign bit is 1. That allows you to detect an overflow. Okay, that's the last slide for today. Thanks for sticking with me until 20 to 3 on a Friday of week 2. I know it's late, I'm sorry about that. And it looks like you're all exhausted and can do with a drink or a sleep or something else, something relaxing. Are there any questions? All cool? All good? Try and get your lab done if you can over the weekend. Do it now. There's less assignments now than there will be in week 5 and 6 and 7 and 8. All right? Sorry? I don't know.